following really. So you have some state vector, let's call it now Q. And it's governed by some, I call it M, but it's really nonlinear, not just in matrix. So it's an nonlinear term of Q state vector. And that's basically a chemistry that contains everything. It's nonlinear everything. And in addition, of course, we have terms which are more like the usual hydro terms. Like this, for example, and the diffusion term that you're all familiar with. Let's call it kappa and something like this, for example. And so I think what we should be trying to do is, and the problem, of course, is that this one is very stiff, so there's a stability problem primarily. If you were to use it in the usual way, these terms would be very large and they would be unstable after the first term step. So this equation has to be treated implicitly. And I think what we should really do is solve this with a separate solver. Or we could maybe make it part of our F array. So part of the F array would be treated implicitly, and the other part would be treated explicitly. So another way how that would look like. So this would then be written in the form, for example, Qn plus 1 minus Q of n divided by u delta t, of course, minus n. And here you would like to write Q n plus 1 plus Q n divided by 2. So therefore this is better in the middle, and therefore this entire thing is accurate to second order. And that's equal to minus Q dot grad Q plus kappa, this one. And the idea is to treat all this at the time, at the old time. For one of the hydro substeps.
And it's going to be first order, right?
Yes, but we can.
That's true.
But on the other, we had, for example, in our current 3n step, we are already doing 3 calls to PDE. In some sense, they are all first order steps, but based on intermediate terms on the right hand side. So if we consider this as part of the threefold third order step, I mean, it's calculated.
I don't think
it's calculated 3 different time levels already. So we could do.
I don't think the resulting scheme will be third order. As I said, it has to be 3 explicit first order steps, and this is not really.
Yeah, I think we can. It's easier to think about this if you think about the second order scheme midpoint. That's what I discussed yesterday.
Yes, the problem also is that sometimes the operator n is non-linear. It's not linear.
That's okay. I mean, so the way to solve this part, of course, so you have something which is a fixed number now, and you can count it. It's a fixed number. You calculate it, and you know this value at each mesh point. So that's given. And this one, everything is freely floating. The Q's are freely floating. These are all at the old end. The main point is that we need to calculate this implicitly because of stability. And this is a nonlinear matrix equation. So you can, let's call it n tilde of Q is equal to the right hand side. And then of course you solve this by saying it's equal to some previous solution plus dn by dq, this would be ij delta qj. And this would be at the old time here.
Thank Axel, you are doing my talk. Perfect.
That's the number. That's what I would mean by what's it called? Newton-Raphson. So
yeah,
Newton-Raphson does not necessarily imply that we ignore the time derivatives. And time derivatives is part of Newton-Raphson. Yeah. So that's how we solve it using even though it's not linear. We just iterate, of course.
That's called the Jacobian method.
And each mesh point separately. There's no coupling spatially anymore.
Can I outline how be the most natural approach. That again has problems with the time scales, with the time order. This, when we do the individual substeps, at that point we say Q n plus 1 is Q n plus delta t, and then, well, at least for the terms here, we say minus u n dot grad q n plus kappa Laplacian q n. So for all the time steps, we just do this simple Euler time stepping, right? Now, if we know, if we have a solver for this, for the problem dq by dt is n of q plus, I don't know, s, r I think we call it, plus r for constant r, if let's do that for constant r, I think that works. So actually we use this here is Rn anyway. That gives us a solution. I probably shouldn't call this Q. Let's see. That gives us a solution Q n plus 1 implicit. Then the increment that we are using here would be, well, if we just did that, we know that instead of this one here, we get something like Q n plus 1 is Q n plus, and then we have Q n plus 1 implicit, and now del, we want that? Yes, delta t times, so it must be divided by delta t minus q n. This is a very fancy way of writing 0 equals 0. So the expression we get at that point here would be q implicit n plus 1, the new value we obtain from the implicit solver, minus q n divided by delta t. And this is now something where, basically that says, we evaluate those terms at the old time, but instead of evaluating this term, we use the information from an implicit solver that doesn't have the time step limitation in order to figure out what we need to put here.
Yeah, okay.
And I think this should work, but if we do it like that, it's only going to be first order accurate in time, just because of that cancellation. And I think it would be worth trying to figure out what we have to do to this term in order to get that third order in time. But that's a different philosophy from what you are suggesting. Also, maybe in the end it turns out to be equivalent. But it would really mean that we call the implicit solver as a subordinate process at some point, just in order to evaluate our right-hand side here.
I mean, I could turn this equation into the second order, and I believe also actually into the third order, the following way. So we just modify this equation by saying instead of having 1, we have 1/2. And here also 1/2. Okay, that's the first part of our double step. And then the next step we say q of n plus 1 minus q of n divided by delta t minus, of course, what's it minus? Yes. And then we have here q of n plus 1 plus q of n by 2 is equal to, and then here the same thing, but then at n plus 1/2. That's
What
it.
you're, that's what you're doing here at factorization, is operator splitting.
Operator splitting?
Yeah,
I mean,
because you
this-
split your
this
you
is
split
what I
your
call-
you split your time advance in 2 times.
I mean, this is going to
Yes,
be
but
quite
not for
different.
different directions or anything.
No, that's not for
Just
different
like
direction,
the
that's
point
that's.
method or
So in
whatever
the
it's
tensor
called.
code we can put NT order. There's a parameter called NT order. You can put equals to 1, 2, or 3.
Yeah.
If it's 1, it's the order method. If it's 2, it's already this method, except explicitly. And if it's 3, it's regular method 3. And we never called such a thing for operator splitting.
No.
I mean, operator splitting is also more associated with X and splitting in X and Y and stuff like this, right?
Sorry, when I say that,
Choose the X direction first and this Y direction separately and stuff.
maybe it's in
So I think if you have a good example, I'm not sure whether these nuclear reactions are really such a good example, but maybe they are.
yeah, tomorrow I can show you some example which seem to work with
So
the
that's
IDI scheme.
Is that actually also chemistry then?
No, it's IDI, it's radiative diffusion, which is deal implicitly after the explicit integration
Oh, I see.
of the rest of physics.
Yes, okay. Yeah, that's probably a different thing, because that is not the diagonal.
It's using the Jacobian Rosenbrock method.
Okay. But as far as your chemistry is concerned, maybe you need this explicit example in place. One can just give it a try with this kind of thing.
Maybe you have to rewrite. Yes. If we deal with this chemistry like that, in fact, we have maybe to code some generic implicit solver.
I think
We give the source term, the result of the explicit time advance, and then we call the implicit solver, and we get Q n plus 1.
Yes. And I believe it's probably a rather trivial extension. I mean, not trivial extension, but it could be a natural extension to the existing scheme. Because at the moment we just have the same scheme, but then this one is always 0. So all we need somehow is some extra layer in the time step routine, which invokes a switch, which means implicit.
Mm-hmm.
And if implicit is invoked, it is understood that the degree of implicity is a local one. It does not cover different mesh points. It just is on the same mesh point. And therefore, at each mesh point, one has to then, of course, sort this matrix.
Yes, what you can do. So maybe we can discuss now about that. This time step actually, you have the 4 sub, you have the IT order, 1, 2, 3, and then you iterate the physics explicitly. Here. Okay? And then finally we get Fn plus 1 equals Fn plus delta t times right hand side. That's right? Mm-hmm. And then what we propose is to this one, so for example, in our case it is this one is the operator n. Okay? So you have something like that, df by dt equal to right hand side explicit plus some implicit operator. Okay? So you did that explicitly in the time step subroutine, and then once you arrive here, you compute a source term, which is n plus 1 minus fn divided by delta t. Okay? And then you solve this equation. So implicit plus source term. And you solve this one using, for the moment, what we are doing is IDI scheme, which is alternate
Directions.
NPC. And the problem is, the question is how much source term should be had in each direction.
Okay.
For the moment we are half of the source term in each direction.
In 2D.
Yes,
Otherwise,
for the moment, and this one is deal with your what we do, the Jacobian Rosenbrock method, which means that finally you have something like that. X something like f n x minus equal 1 plus lambda y fn plus the source term divided by 2 in the x direction, and in the y direction it's this one. X divided by 2. That's the IDI scheme, which is a factorization. And this operator is nonlinear, because in our case it's something like the divergence of k of t grad t.
Yes. But it's only one dimensional. It's
In
not-
each direction, yes.
Yes, and therefore it's of course possible. Yes.
But this one is, can be coded in a more generic form, something like a call IDI, with just after the time step, explicit time step here, called IDI, where we can give the source term and the new function for any source term.
But the difference is that in your case, you have, at the different chords, you actually have different operators.
Yeah,
Whereas here, we have the same operator all the time.
that's true. In our case, the operator should be updated every
Yes.
time step.
I mean, it
But
should
we
also
have
be
to-
updated in our case, but the nature of the operator is the same.
Exactly.
One. You
But-
have different right-hand sides each
True,
at the
but
same time.
what I said is that it can be maybe a good idea to put some generic implicit subroutine where people can code their own stuff,
Mhm.
but the code will be the same. That means that here the explicit physics, that's the source term, and then that's the F array, and the array of the whole, including the whole field. So it's finally simple. Huh? The problem is that actually we are not committed that because we put that in a time step subroutine, and it's a call with the flag L underscore ADI.
Mhm.
L underscore. So if you have this flag which is true, you iterate implicitly the rotative diffusion.
Right.
And finally, I think your chemistry problem can be dealt with exactly the same thing.
So we basically have now two suggestions that really are sort of stacking the implicit and the explicit solvers differently, right? I think my suggestion is probably most likely identical to Axel's suggestions, just different ways of writing that. I suggest a simple test problem to see whether the time order, whether you, I think you still get only first order with this one here. And the simple test problem would be,
No, because you can put n equals to 0 and you recover what we always did.
yes, but as soon as the implicit stuff starts to play a role, I think the time order degrades. The test problem would be to set n equal minus gamma, well, n of q equals minus gamma q, and then replace the implicit solver with simply using the analytical solution. So what's the nomenclature for that one? Not sure, but anyway, we know that has an exponential decay solution, and we can hook that up with some not too trivial velocity field, and then just see what time order we get. I suggest this because that's what you get for the electric field if you want to do relativity. You have this exponentially very fast, in a conducting medium, this very fast decay of the electric field that doesn't care about what is anywhere else. You can treat that locally as just an exponential decay. And that's when I came across this phenomenon that if we do too good at the sub-steps, we might get lower order in the combined scheme. That probably can be remedied. I think if we try this, we only get first order. Most likely Walrus, if he tries this, although maybe that's a bit too special to draw final conclusions, would get second order.
I mean, as you know, our scheme, the 2n scheme, is already actually only accurate to a third order with respect to the linear terms. So the nonlinear terms were never really treated as a third order.
Are you sure?
I think so. I mean, obviously, our method is not a standard Rumikuta, which would require 4n slots.
That doesn't matter. I mean, there's many different third order 3-step Rumikuta schemes, and the question is ours one of them? Also not the one that you normally find in the literature, the 1 or 2 that you really find if you look at Brownwoods and Sagan, for example, or is it one that is not truly third order?
I was simply under the impression, and I thought we always thought that this is the case, that we have. I mean, we don't have a general family of different coefficients in our scheme. We can continuously change the coefficients, and still we are third order with the scheme. But only with respect to the linear term.
I mean,
if this gamma is a constant, that is.
Anyway, I have the order conditions for Rumikuta scheme somewhere, and I can figure out whether our scheme is truly third order or not. Yes. I'm not sure whether linearity. Yeah. Okay. Yeah.
And by the way, not to worry anybody. I mean, the reason why a third order scheme is better than a first order scheme is, of course, because mostly of the linear terms in the equation, the transport terms, for example, or linear at least, because they are the ones which restrict the time step. And so with the third order scheme, one can allow oneself having longer time steps, up to 0.4 times the current condition. That's one of the reasons why our scheme is good. Longer time steps. You can always
and put differently, if we had much higher order in time, well, having high order in time is what you profit from having high order if you use a very small time, if you use a small time step. But we will always try to use a time step that is not too far from the maximum allowed time step for the given resolution. We still get convergence if we increase the resolution, but we will never want to use a time step that is way smaller than the maximum stable time step. And so
it would not even make things more accurate, as I think is known. If you take half the length of the time step, you have half the error per time step, but you have more time steps, and the end result I think is the same.
No. I mean, that would be a zeroth order scheme. I mean, that's the whole thing about order. If you have a first order scheme and you half the time step, you have 1/4 of the error. So if you do the integral of the same interval, you still get 1/2, and with the third order scheme, you would get 1/8. But while we try to decrease the delta x to the extent that computer time permits, we do not try to separately decrease delta t because we want a delta t that does the right thing, and increase accuracy doesn't really Okay, shall we move on to the next talk, and let's plan to see you again.